All right, then I guess we can begin. Welcome back to quantum field theory. Today we will discuss various processes in QED, quantum electrodynamics. And before we go to the actual processes, I want to interject a small section where we simply discuss techniques for gamma matrices, because that is obviously important to do actual calculations. And I will focus here only on very basic techniques for gamma matrix calculations and not do the full theory in all generality, but do it in a way which is sufficient for us in these weeks. All right, here I collected once again the basic properties of gamma matrices. First of all, there are gamma mu matrices, which are of course the basis of representation of the Lorentz group on space of Dirac spinors. And the Clifford algebra relationship is this one. The anti-commutator between two gamma mu matrices gives 2 times the metric tensor times the unit matrix on spinor space. Then there is a gamma 5 matrix which anti-commutes with all the gamma mu's, and gamma 5 can be constructed as the product of all gamma mu's, gamma 0 up to gamma 3. And gamma 5 square is the unit matrix. And then there are a few relationships for the Hermitian conjugate, complex conjugate, and transpose of the gamma matrices. Here I only write down the one for the transpose. Gamma mu transpose can be obtained by this charge conjugation matrix multiplied from the left and the right with the gamma mu matrix. Okay, and with these properties you can calculate and help to calculate many traces which appear in actual calculations, and that is what I want to focus on now. And let us start with 2 simple examples. And the first simple example is this one, namely the trace of 2 gamma matrices, gamma mu, gamma nu. How do we compute this trace? We use basically for all the traces similar ideas as we used for those contraction rules from which we derived Feynman rules. Namely, we always take one gamma matrix and commute it as much as we can to the right until we get some relationship. And while we do this commutation to the right, we always pick up this anti-commutator which has a known result, where on the right-hand side there is no gamma matrix anymore. So by using the anti-commutator, we reduce the number of matrices by 2 in such an expression. That is our strategy. So applying this strategy here, we do the following. We write gamma nu as 2 times the metric tensor minus the opposite order. Okay? So that is an obvious equality because of the relationship. And here we now have a number times the unit matrix in the trace. So therefore, this gives simply 8 times the metric tensor, because the trace of the unit matrix is 4, since we have 4 by 4 matrices. And that is minus the trace of gamma nu, gamma mu, which is the opposite order. Good. Why does that help? Because now we can use cyclicity of the trace, which means that we can take the last matrix and put it into the front because of cyclicity. And then we have here the same trace as we do on the left-hand side of the equation with a minus. And therefore, if we bring that trace over here, we have 2 times the original trace is 8 times metric tensor, and therefore we can derive that actually our original trace is equal to 4 times the metric tensor. And then we have computed it. That is the strategy. And we immediately apply the same strategy to a more complicated trace with 4 gamma matrices, gamma mu, gamma nu, gamma rho, gamma sigma. So we use exactly the same strategy. We take the gamma mu on the left, use the anti-commutator here, afterwards here, afterwards here. Then we get the trace with mu, rho, sigma, mu Then we use cyclicity and bring the gamma mu back to the front and obtain a similar relationship here. So if we do that, then we first have here 2 times the metric tensor G mu nu times the trace of gamma rho, gamma sigma from the anti-commutator between the first two, minus the trace where the gamma mu is at the second position. Right? So here we have used the anti-commutator between the first two matrices. Next, we use the anti-commutator between gamma mu and this one to bring it to the third position. Then we have here this minus 2 times the metric tensor between mu and rho times the remaining trace of gamma nu, gamma sigma. Then we get plus the remaining trace where we have the order gamma nu, gamma rho, gamma mu, gamma sigma. So gamma mu is at the third position now. And we have picked up 2 terms with a trace of 2 gamma matrices. Then our strategy tells us to use the anti-commutator once again, put it at the fourth position. Then we get the first 2 times G mu nu times the remaining trace gamma rho, gamma sigma, minus 2 times G mu rho times the remaining trace gamma nu, gamma sigma. Then from here we get plus 2 times the metric tensor G mu sigma times the remaining trace of gamma nu, gamma rho. And then we get minus the final trace, which is gamma nu, gamma rho, gamma sigma, gamma mu, where gamma mu is now at the last position. And then we see we can now use cyclicity, put the gamma mu at the front, and we have here the original trace with a minus. So if we put this trace here to the left-hand side of the equation, we get 2 times the original trace is exactly the sum of the 3 terms, each term with a metric tensor and a trace of 2 gamma matrices only. So we can divide by 2, and then we have computed our original trace with 4 gamma matrices, because also the traces with 2 gamma matrices are known. They just give the metric tensor. So the result of this trace with 4 gamma matrices is a combination of 3 terms. Each term consists of 2 metric tensors such that the 4 indices are saturated, and we get plus minus structure depending on basically the permutation of the indices. So if we write down the full result here, then we get trace of these 4 gamma matrices is the following. 4, the 4 comes because of the trace of the unit matrix 4 times, and then G mu nu, G rho sigma minus G mu rho, G nu sigma plus G mu sigma, G mu rho. This is how you can compute such traces, and that is the general strategy. You see that in the same way you can compute traces with arbitrarily many gamma matrices as long as the number is even. If the number is even, then you will always get this thing that at the final term you get the original trace with a minus, you put it back to the left-hand side, and then you get a recursion formula where you can replace a trace with an even number of gammas by traces with 2 times gamma matrices less. And in this way you can get an algorithm with which you can compute all traces. And so, having this in mind, let me just summarize with not so many comments anymore the most important traces. So, trace of the unit matrix is of course 4. Trace of product of 2 gamma matrices is 4 times the metric tensor. Trace of 4 gamma matrices is what we just discussed. 4 times this combination. Then we can, and so on. With an arbitrary even number of gamma matrices can be computed similarly. Now, the next thing is what happens if we have an odd number of gammas. That is actually 0. And just to give the reason, insert gamma 5 square and use cyclicity. If you insert gamma 5 square, then you can use cyclicity. Then you have gamma 5 at the two opposite ends here of the trace, and then you use an odd number of times the anti-commutator of gamma mu with gamma 5, and then you see that the trace must be equal to minus itself because of an odd number of anti-commutation relations. And since it must be equal to minus itself, it must be actually 0. Then the trace of gamma 5 is 0. Trace of gamma mu, gamma 5 is also 0. And here you can, for example, insert gamma mu contracted over mu. Let's call it gamma rho, which is 4 times the unit matrix, because that is equal to its, so the order doesn't matter, therefore you can replace this by the anti-commutator, but the anti-commutator is the metric tensor, so you get a metric tensor G rho, which is 4 times the unit matrix. So that you can insert this 4 times the unit matrix into the trace, and then use again cyclicity and anti-commutation relations, and then you see that the trace must be equal to minus itself or something like this, and therefore these two traces must be 0. However, this trick does not work if you have here 4 gamma matrices. Gamma mu, gamma nu, gamma rho, gamma sigma, gamma 5, that is actually non-zero. And so it goes on, traces with gamma 5 and more than 4 gamma matrices, they are in general non-zero. And then a last remark, gamma mu 1, gamma mu n is equal to the trace of gamma mu n, gamma mu 1. So where the order is simply reversed, completely reversed order. Use this c gamma mu c to the minus 1 is equal to minus gamma mu transpose. So if you plug in the c and c to the minus 1, so you can just insert into the trace the matrix c times inverse of c, which is the unit matrix. Then you can insert this between all the gamma matrices. Then you see the trace is equal to the trace where you replace all of them by their transpose version. Then the trace is equal to the trace of the transposed matrix, and then you simply reverse the order. And that, of course, is anyway only non-zero and therefore meaningful if n is even. Okay, this should be sufficient for us for the moment. And the derivations are obvious in all these cases. So I don't know whether you have some questions to this from your experience and exercise sheet. You have seen some of those traces. So if you have some issues with them, then let me know. Yes. Yeah. So this is, okay, so a more elaborate thing that would be equal to 1/2 times G rho plus gamma rho. Okay, so that is obviously the same thing. And then you see that here the anti-commutator is generated. And the anti-commutator between the two is the unit matrix times the metric tensor G rho rho. If you contract the metric tensor G rho rho, you get 4, the number of space-time dimensions. That's simply the trace of the metric tensor with up and down index, which is just the unit matrix. Yeah, but if you have G rho rho with upper and lower index, that is equal to the Kronecker delta. So the trace is 4. That is the reason. Okay, good. Then let us now come to physics. Let us discuss a first process in QED in some detail. So we are looking at the same process that we are looking at the exercise sheet at the moment, where we have a fermion, anti-fermion going into a different fermion, anti-fermion pair. And we discussed the process at tree level. And of course, the physical examples are electron-positron going to mu plus, mu minus, or the opposite, mu plus, mu minus, going to electron-positron. And there would be many similar processes as well. Those are important processes where this process means that you take a light particle, and if you have sufficiently high energy, you can create a pair of particle-antiparticles of heavier rest mass. So there is a threshold. You need to surpass a certain energy threshold in order to be able to produce those. If you just surpass the energy threshold by a very little bit, then those particles will be produced more or less at rest with very small kinetic energy. And if you go to even higher energy, then you can produce these particles even with relativistic velocities. Here, that is also interesting. You take a heavy pair of particles, they collide, and of course in the collision you can obtain a pair of very light particles. And so in the extreme case, even if they collide more or less at rest, those final state particles will be immediately relativistically high energetic. So those are interesting processes, and in order to describe them, we need to extend QED in a trivial way to contain a different type of particles. And we focus here on E plus E minus 2 muons. And the muons have the same charge as the electrons. Okay, then let us begin with our first subsection, where we look at the TFI matrix element. So the scattering matrix element for this process. And for this process, there is a single Feynman diagram at tree level. And this Feynman diagram should be known to you. So it looks like this. This type of Feynman diagram. So we have here in the initial state an E minus, where we have an incoming momentum P1 and spin S1. Here we have an incoming E plus. The arrow goes into the opposite direction to indicate that it is an E plus particle, but the momentum flows inside into the diagram, and we call the momentum P2 and spin S2. Then here we have a photon propagator with momentum Q, which is the sum of P1 plus P2. And in the final state, we have on the one hand mu1, u minus, with outgoing momentum P3 and spin S3. And on the other hand, we have an outgoing mu plus, indicated by that reversed arrow here, with outgoing momentum P4 and spin S4. And at each vertex, momentum is conserved. So therefore, at this vertex, we learn that Q is the sum of P1 plus P2. But at that vertex, we learn that also Q is equal to P3 plus P4. And so obviously, the sum of the initial state and final state momenta are conserved. So this is our Feynman diagram, and our task is to compute it. The diagram itself will immediately give us I times the TFI matrix element. And afterwards, when we want to calculate the probability, we need to square the matrix element and so on. But let us first write down the matrix element, the T matrix, which is a probability amplitude, quantum mechanically speaking. So I times TFI, what is the value? From the standard Feynman rules of QED, which you now know. So we start, we have two fermion lines, and for each fermion line, the rule was that we have to go against the arrow along the fermion line and write down all the Feynman rules in the appropriate order. So if we do that for the electron-positron line, then we need to start here and write down the spinor for the incoming positron, which has the value V bar of the incoming positron, and let me immediately abbreviate this with simply V bar 2, where 2 stands for the argument P2 and S2. The next Feynman rule is the one for the vertex, which is minus I EQ, where we introduce a notation that we assign a Lorentz index mu here at this vertex, and we will assign a Lorentz index nu at the other vertex. So then we have that vertex, and then we have the Feynman rule for the incoming electron, which is U1, a spinor with argument P1 and S1. Then we have the Feynman rule for the photon propagator, which is minus I times G mu nu divided by Q square. And then we have the Feynman rule for the muon, anti-muon line. Starting against the arrow, we first have to write down the spinor for the outgoing mu minus, which is U bar 3. Then the vertex minus I EQ gamma nu now. And finally the spinor for mu plus, which is V4. That's all. And so to structure it, you see that we have here some term which corresponds to the electron-positron line, some term or factor corresponding to the mu plus mu minus line, and a factor for the photon propagator. And so to highlight the structure even more, let us introduce some notation. We use E mu. So first of all, let's say TFI without the I. What is it actually? So how many I's do we have? We have here on the left-hand side 1 I. On the right-hand side we have minus I times minus I times minus I gives plus I. So therefore the I and the minuses simply drop out. And when we write out TFI without I, then we can simply say that is equal to some electron stuff, E mu, times some muon stuff, M nu, times the photon propagator, P mu nu, and where all these abbreviations are as follows, namely E mu for the electron is now the thing without the minus I, V bar 2, E times Q times gamma mu times U1. For the muon M nu, we have E times Q times u bar 3 gamma nu v4, and the photon propagator p mu nu is simply g mu nu divided by q squared. And so we have beautifully separated our T matrix element into the three factors corresponding to the three elements. Each of these elements is now essentially real up to maybe the spinors being complex valued, but it's essentially real and has nice Lorentz transformation properties. And so in this form, it is very straightforward to discuss further what happens in the calculation. So building on that structure, we can now go to the next step. So there is not much we can evaluate here. Of course, in principle, we could put in numerical values for the spinors and momenta and so on, maybe in a computer. But what we will now focus on is the square of the amplitude, because the squared amplitude in quantum mechanics gives us probabilities which are physically measurable. And so let us discuss the TFI square in the unpolarized case. So, first the square. TFI, absolute value square, is simply the thing times itself complex conjugated. And using the structure, we can write it like this. Let's say we start with E mu, then E complex conjugated mu prime. Then times m nu, m complex conjugated nu prime. Then propagator p mu nu times propagator p star mu prime nu prime. That is the absolute value square. And we can introduce yet another set of abbreviations, namely this thing here is now a tensor. Let's call it E mu mu prime, a tensor. And that is also a tensor, m nu nu prime. And that we leave. Okay. And so we have here introduced what one might call electronic tensor. And that would be the muonic tensor and so on. And we can discuss those tensors individually. So what is necessary to know is now, how do you obtain the complex conjugated of such an expression? The expressions here, they involve gamma matrices and spinors, and so you need to know what is the complex conjugate of such an expression. Therefore, that is a necessary building block. For example, U bar gamma mu V complex conjugated. What is that actually? And what is it? First of all, you have to realize that that object here is a complex number in general with an index mu. But from that point of view, from the gamma structure point of view, star is therefore the same as a dagger, because it's a number, therefore transposition doesn't do anything. But if we dagger it, then of course we can write it like this: V dagger, gamma mu dagger, U bar dagger. Then we can insert gamma zeros, and then we see that this is actually the same as V bar gamma mu U. And so the complex conjugate of such an expression can be easily evaluated if you know that relationship, that gamma mu dagger is connected to gamma mu by multiplying from the left and right with gamma zero. So, plugging in this, we then learn what is our electronic tensor, for example. E mu mu prime would be the following. So the original thing is that we have here E times Q square. Then V2 bar gamma mu u1. And then the complex conjugate is u1 bar gamma mu prime v2. And here we can now apply Casimir's trick, where we say that actually if we have such a number, we can write the number as the trace of itself, but the trace is cyclic. And if we use cyclicity of the trace, then we can put the v2 bar at the end, and we can write it as gamma mu u1 bar gamma mu prime v2 bar. And then we have here traces of 4x4 matrices. So this object here can be regarded as a 4x4 matrix. That object can be regarded as a 4x4 matrix. And so here we now have a trace of a product of 4x4 matrices. And that is a simplification because it's not yet a simplification, but it will become a simplification once we use that we work in the unpolarized case, and we will do a summation over all the possible spins of all particles. Because then we know something about the sum over all spins of this exact combination here. So that is the unpolarized case. So we use, for example, sum over S1 of this object u1 bar is equal to P1 slash plus the electron mass, and so on, right? This is what we now can use, and that can go into this. And so therefore, we have unpolarized tensors, for example, concrete for the electron tensor. We sum over the possible spins, because we do not care anymore about the spin orientation of all the particles. So we want to know the overall probability for any E plus E minus going into any mu plus mu minus, regardless of the spin. That is the physics question that we have. And okay, so the possible spins, because we do not care anymore about the spin orientation of all the particles. So we want to know the overall probability for any E plus E minus going into any mu plus mu minus, regardless of the spin. That is the physics question that we have. And okay, so therefore we do the summation over the tensor E mu prime. And then we can simply replace here in the trace the UU bar, VV bar expressions by those completeness relations. And then we obtain E times Q square times the following trace, here in this case gamma mu, then P1 slash plus the electron mass times gamma mu prime, and then P2 slash minus the electron mass. That is our electronic tensor. And that is now a trace of a combination of gamma matrices. And if you look at the trace, then you see up to 4 gamma matrices. Gamma P slash is a trace of 4 gamma matrices. But there is also the term with M square, which then involves only 2 gamma matrices. And all these traces, of course, need to be evaluated. So, and now I would say that is your exercise, right? And so if you do not see any difficulty in doing that yourself, then we can directly write down the result. Do you want me to do 1 or 2 intermediate steps? Somebody? Okay. Then 4 comes from the trace of the unit matrix, E times Q square, and then we have the following. So we have here P2 mu prime times P1 mu minus G mu prime P1 P2 scalar product plus P1 mu prime P2 mu minus electron mass square times metric tensor G mu prime. So we have 4 terms. Why 4 terms? Because the thing with 4 gamma matrices gives us 3 terms in the result, and the term with the mass gives us just 1 term in the result, and the trace of the products of 3 gamma matrices vanishes, and therefore we get exactly those 4 terms here. So then we have calculated our spin-summed electronic tensor, which is now explicitly given in terms of momenta. So there are no spinors anymore, no gamma matrices anymore, only momenta, and therefore it's a quite simple expression that we could numerically evaluate easily and that we can also understand physically. And of course, the muonic tensor can be treated analogously. So here, mu prime gets the basically same result, only with the replacement P2 becomes P4, P1 becomes P3, and so on. And the indices mu become nu. So I just copy this. P4 nu prime, P3 nu minus G nu prime, P3 P4 plus P3 nu prime P4 nu minus m muon mass square G nu prime. So and then we have
طيب يمكن أن نسأل سؤالا في هذا الموضوع. طيب نحن جبنا التنسور في الميو والتنسور للميون والتنسور للإلكترون. بعد ذلك عندنا البروباجيتور بالنسبة للفوتون. طيب السؤال الذي يطرح نفسه، أين المقام هنا؟ فرضنا كثيرا أنه عند العلاج يجب أن تكون المقام أعلى من البسط. أين المقام هنا؟ وما الذي يعبر هنا عن الفضاء ثنائي الأبعاد غير متناظر؟ وما الذي يحتويه هذه المعادلة؟ الأمر واضح جدا. كل ذلك عبارة عن كما قال intermediate equations، وكلها تختصر مع بعض في النهاية تعطينا معادلة دالة في البيث اللي هو كميات التحرك. هذه المعادلة تعبر عن الطاقة المطرودة من التفاعل بدلالة الطاقة الداخلة من التفاعل أو كمية التحرك الداخلة من التفاعل. يعني مثلا عندنا بالنسبة للإلكترون B2 اللي هي كمية تحرك البوزيترون، B1 كمية تحرك الإلكترون مضروب في B1 B2 في G ميو. هذه معلومة مهمة، لكن أنا حاليا لا أستحضر ماذا تعني هذه المعلومة، لأن G ميو نيو وليست لم توضع اعتباطا ولديها تفسير في نظريتي أنا، خصوصا المعادلة المترية تعالى يوسف. ممكن نشوفها، تعالى نشوف هذه المترية طبعا جزء من المترية تعالى يوسف، دي ار على سي دي تي. انظر لجي تي تي وجي ار ار، هذا عبارة عن متريك تنسر. جي تي تي متعلق بالزمن وجي ار ار متعلق بالمكان. فإذا جي تي تي إذا جي ميو نوت لم توضع اعتباطا. يعني هنا هذه الجيز لم توضع اعتباطا، إنما تدل على شيء معين. طيب زائد بالنسبة للمعادلة الحد الثاني أيضا بي ميو برايم بي 1 ميو برايم بي 2 ميو برايم ناقص. هنا ظهرت الكتلة، وننظر الكتلة مضروبة وين؟ أيضا في جي ميو أيضا الكتلة مضروبة في جي. ولاحظ أن الكتلة في علامة ناقص. هذه معلومات أيضا يجب أن نلاحظها، أنه هذه المعادلة تخبرنا عن حدود مختلفة يعني مباشرة، يعني طاقة مطرودة من التفاعل، والحد الموجب مثلا طاقة موجودة في التفاعل، والحد السالب هي طاقة مطرودة من التفاعل. لكن لاحظ أنها كلها بدلالة الطاقة على داخل التفاعل. أيضا في معادلة الميون أيضا نجد الجي ميو أيضا الام مع الجي ميو أيضا، وهي عبارة عن طاقة مطرودة من التفاعل. الميون طاقة مطرودة من التفاعل، والإلكترون طاقة داخل التفاعل. لكن أيضا ربما هناك اختصارات أكثر. هذه المعادلة تخبرنا طاقة داخل التفاعل وداخل الطاقة مطرودة من التفاعل. طبعا هذه معادلة جميلة جدا، يمكن أن نقول أنها يمكن أن تخبرنا بالصيغة الكاملة للتفاعل، لأن هي عبارة عن طاقة داخل التفاعل. يعني الإلكترون والبيزيترون عبارة عن طاقات داخل التفاعل، والميون عبارة عن طاقات مطرودة من التفاعل. وبالتالي هذه المعادلة ممكن تعطينا صيغة كاملة للتفاعل، لا تعبر فقط عن طاقة مطرودة من التفاعل. إذا وقف على هذا، لكن ربما يكون هناك اختصارات. والاختصار بالمناسبة الكيو تعتبر قيمة مجهولة، تعتبر قيمة مجهولة، ولذلك يجب أن يكون في هناك مزيدا من الاختصارات. يعني هنا الجي ميو نيو هذه معروفة، لكن على كيو سكوير هي كمية لا يمكن قياسها. إذا مفترض أنه تكون هناك مرة أخرى هناك اختصارات هي تابعة. هذه ليست المعادلة النهائية، يجب أن تكون هناك اختصارات أكثر. فربما الكيو يعبر عنها من هنا، ربما كتبها هنا. نعم، الكيو يساوي بي 2 زائد بي 1، وبالتالي كيو سكوير معناتها بي 2 زائد بي 1 سكوير يعطينا بي 1 سكوير زائد بي 2 سكوير ناقص زائد بي 1 مضروب في بي 2. بالتالي يمكن اختصار البي 2 يمكن اختصارها مع المعادلات الأعلى. تعال نشوف ماذا سيصل. لكن في النهاية هذه معادلة جميلة تعبر عن طاقة داخل التفاعل وطاقة مطرودة من التفاعل، وحدودها واضحة وجلية. معادلة حد كيو تربيع يجب أن نجد له حلا. الجي طبعا هنا يعتبر واحد، أنا نظريتي لا تعتبر الجي واحد، أو هنا تعتبر 4، 1 ناقص 1 ناقص 1 ناقص 1 هكذا 3 أظنه. لكن في نظريتي لا، الجي تتغير تغير كبير جدا بوجود الكتلة وعدم وجود الكتلة. فبالتالي نظريتي تستطيع أن تقدم تفسير أشمل من هذه النظرية، هذه المعادلة. لكن تعالوا الآن نشوف بقية الحل، وبعد ذلك نأتي نحكم.
Tensors, and what we then can do is we can explicitly work out the squared matrix element TFI square after summation over all the spins. So we can plug back in those results here into that product. So we get the product of the muonic and the electronic tensor with the propagators, and the propagators are also simply given by momenta 1 over q square times the metric tensor. So the metric tensors over there, G mu nu, they simply mean effectively that nu becomes mu and nu prime becomes mu prime, so they are contracted. And therefore the main thing that we have to do is to contract this object with that object. simply contracted. And so we get a contraction of 4 terms times 4 terms gives 16 terms, but they can obviously easily simplify it because many of the terms are equal. So there are not so many different momentum combinations which can appear in the result. Therefore, doing the contraction, so you will get, for example, one term from here, P2 times P4, after nu prime becomes mu prime, right? P2 times P4 times P1 times P3. Then if you do the contraction of those two terms, you get exactly the same. P2 times P4 times P1 times P3. So those two contractions already are equal. Then you get some mixed terms that contracted with this is P2 times P3 and P1 times P4 is the opposite combination. So all sorts of scalar products appear and you have to collect and get some final result. And I will now immediately jump to the final result because summing these 16 terms and simplifying is not particularly deep. So I believe that you can do it yourself. Therefore, I need to copy it here from my sheet. The result in 4 dimensions is the following, namely sum over S1 up to S4 of TFI square is the following: 8 times EQ to the 4th power divided by Q to the 4th. That is our prefactor, and the prefactor is first of all obvious. E times Q square for each of the factors gives in combination E times Q to the 4th power. And from the propagators we get Q square squared gives Q to the 4th power. And the 8 I factored out after looking at the full result. And then from the contractions we get the following. First of all, I use the abbreviation Sij is the scalar product of two momenta Pi dot Pj to simplify the notation, and then we get 4 times S13 S24 plus S14 S23. Those two are exactly from the example that I just mentioned, from the contraction of the first terms and from the second terms and the cross terms. That gives exactly this. And then from all the rest, we get the following: plus 2 times the sum of the electron mass square and the muon mass square times Q square. That's all. Okay, so it's not particularly involved. Here, in order to see the Q square, you have to use a relationship. Let's say Q square is of course P1 plus P2 square. That is actually the electron mass square plus 2 times S12 in that notation. But it's also the same as P3 plus P4 square, so it's also equal to muon mass square. So 2 times muon mass square plus 2 times S34. So you can replace Q square in 2 ways. And in order to see that Q square arising, you need to use both relationships for Q, because from that expression you will see on the one hand such a term arising which becomes Q square. You will also see such a term arising which also becomes Q square, and then you can collect all the Q square terms in that way. So that is the result for the spin summed total probability of the process. And the calculation you can do yourself. And now we can discuss some physics aspects of the result. But before discussing the physics aspects, you have the opportunity to ask me some questions if you want me to highlight some details of the computation.
طيب جميل جدا. أول شيء ننظر إلى شحنة الإلكترون أسي 4، يعني 10 أس ناقص 19 أسي 4. هذه طبعا كمية صغيرة جدا جدا. الكيو ربما تكون كبيرة، لكن في النهاية بالنسبة لأبعاد لأنها ستكون كمية صغيرة لتعادل الشحنة. نأتي هنا مجموعة من البيس اللي هو اللي هو كميات التحرك مضروبة في بعض ومجموعة مع بعض، B1 B2 B3 B4 وهكذا مجموعة مع بعض، زائد هنا ما في ناقص 2 M تربيع مضروبة أيضا في Q تربيع، والكيو أيضا عبارة عن مجموعة من البيس مضروبة في بعض أو مجموعة في بعض. نجد في حد المقام هنا المقام جميل، لا يوجد شيء. المهم وهي المعادلة جميلة عميقة، لكن نرى أن الحدود التي تكون متناقضة اللي هي علامة ناقص انتهت عن طريق الكونتراكشنز. هذه تعتبر طاقة مطرودة من التفاعل وليس داخل التفاعل، لأنه كان هناك حد ناقص وسيل الحد الناقص غير موجود، موجود فقط علامة زائدة. الحدود كلها موجبة، البروبابيلتي يجب أن تكون موجبة طبعا، لا يمكن أن تكون هناك ناقص، لكن يمكن تكون مكون من حدين، حد موجب وحد ناقص. الحد الناقص يعمل عكس الحد الموجب، وبالتالي يخبرنا عن التغير في معدلات التدفق أو التغير في الطاقة الداخل والطاقة الخارجة. بالمناسبة هنا استخدمنا نوع من السيمتري اللي هي السيمتري الدلتا، أن جعلنا أنه كمية التحرك الداخلة هي نفس كميات التحرك الخارجة من أجل الكونتراكشنز طبعا، وهذه معلومة مهمة جدا لكي تخبرنا أن هذه عبارة عن طاقة مطرودة من التفاعل بمساواة هذه كميات التحرك. طيب أنت سويت كمية التحرك، من يتحمل الغلط أو من يتحمل الاختلاف؟ هي الكتلة. لهذا نرى أن كتلة الميون أكبر من كتلة الإلكترون بكثير، يعني هنالك شيء خطأ، وأنا أقولها بكل صراحة، هناك شيء خطأ في هذه المعادلة. هذا الخطأ لم يظهر كخطأ، وإنما ظهر كشيء غاب عننا. ما هو شيء غاب عننا؟ هو الكتلة. كتلة الميون يا سادة أكبر من كتلة الإلكترون ب200 مرة، والآن هي موجودة هنا. كتلة الإلكترون زي كتلة الميون، هذه هي كتلة الإلكترون تربيع زي كتلة الميون تربيع، هي أكبر من كتلة الإلكترون ب200 مرة. هذا يعني أننا عندما استخدمنا هذا السيمتري اللي هو كمية التحرك الداخلة يساوي كمية التحرك الخارجة، هذا السيمتري الذي أدخلناها، فأخبرنا أنه الخطأ تحملته الكتلة، فلم نستطع تتبع الكتلة. فقط اكتشفنا اكتشافا أنه هناك خرجت جسيمات تحمل كتلة، طبعا عن طريق التجربة ليست عن طريق المعادلة. المعادلة لا تخبرنا بذلك، لكن أخبرتنا التجربة أن هنالك كتلة ضخمة جدا جدا خرجت تعتبر 200 مرة ضعف كتلة الإلكترون. هذه ما أخبرتنا عنه التجربة، وبعد ذلك عوضنا في المعادلة بكل أريحية وحسبنا البروبابيلتي اللي هو البروبابيلتي امبليتيود. لكن هذه البروبابيلتي امبليتيود هي ليست النتيجة النهائية. النتيجة النهائية هو الكروس سكشن. الكروس سكشن هو النتيجة النهائية، لأنه يساوي البروبابيلتي امبليتيود مضروبة في شيء مقسوم على شيء، يعني احتمال ربما يكون مضروبة في مقسوم على زاوية مجسمة، شيء من هذا القبيل. هذا هو الكروس سكشن مضروب في شيء. فالكروس سكشن هو النتيجة النهائية، هو ما نراه في التجارب، لكن البروبابيلتي لا نراها في التجارب، إنما نحسبها حسابا من الكروس سكشن. يعني خصوصا إذا دخلت فيها زوايا، اللي هو زوايا البولاريزيشن وما إلى ذلك. إذا دخلت فيها هذه الزوايا، فهذه الزوايا تخبرنا بالكروس سكشن بكل وضوح. هنا أيضا يخبرنا الكروس سكشن لكن في جميع الاتجاهات. طيب هذه الطاقة مطرودة من التفاعل. استخدمنا سيمتري اللي هو كميات التحرك يجب أن تكون محفوظة. هذه سيمتري جنت على الكتلة وجعلت الكتلة غير ملاحظة، غير متنبأ بها. وعندما نقول غير متنبأ بها نقصد تطور الكتلة، ويجب أن نراها في التجارب. أنا طبعا تقدمت كثيرا في كتابي الحلقة 54، واكتشفت في شيء غاية الأهمية أن القوى اللونية والفعل degrees of freedom أحمر أخضر أزرق ما هي إلا قوى مغناطيسية. ولاحظ أن المغناطيس أيضا يحتوي على الكتلة ويؤثر على الكتلة بالمناسبة. بالتالي بما أن هي عبارة عن قوى مغناطيسية وتحمل في طياتها الكتلة، فهذا يعني أننا نستطيع تتبع الكتلة عن طريق تتبع الخواص المغناطيسية للتفاعلات. طبعا هذه الخواص المغناطيسية للتفاعلات صعبة جدا، لأننا نتكلم عن حدود صغيرة جدا 10 ناقص 18 متر. لكن في النهاية أنا بضع النظرية والعلماء سيبحثوا عن الحل تكنولوجيا وتقنيا. أنا بضع النظرية فقط، لكن فسرت القوى اللونية والديجريز اوف فريدوم لها هي ليست قوة خاصة بها، وإنما هي تفاعل بين السترينج ستنسور والفضاء. لأنه في الفيديو السابق رأينا أن السترينج ستنسور ما هو إلا كيرفتشر. بالتالي هذا السترينج ستنسور اللي هو اف ميو نيو هو الذي يتغير في الفضاء ويتشكل في الفضاء ويظهر من هذا التشكل مجال مغناطيسي قوي جدا جدا. هذا واضح. يعني أنا أخذ مني زمن حقيقة، أخذ مني زمنا كبيرا يعني منذ بدأت كتابة الكتاب. لكن ما فاتني هو أنه عندما ننظر للنجم النيوتروني نظرا أن له خواص مغناطيسية أكبر من الخواص الكهربائية. النجم النيوتروني عبارة عن مغناطيس ضخم جدا جدا. إذا مع وجود الكتلة ووجود طاقة التفاعل فإن المغناطيس يتضخم ويكون خواص المغناطيسية تكون ضخمة جدا جدا أكثر من الخواص المجال الكهربائي. هذا ما فاتني حقيقة، أنا هذا ما فاتني. فبالتالي مفترض أن أعبر عن القوى اللونية بمجال مغناطيسي. أمر بسيط جدا وسهل جدا جدا، لكن فاتني كثير. الحمد لله، شكرا لله. أنا أعتبر هذا توفيق إلهي أن الأستاذ تحدث في الفيديو السابق لهذا مباشرة، تحدث عن السترينج ستنسور وعلاقته بالكيرفتشر. لولا هذا لكان أخذ مني زمنا أكبر. لكن الحمد لله حديث المحاضرة عن السترينج ستنسور الاف ميو نيو وعلاقته بالكيرفتشر اللي هو ريمان ميو نيو، هذا ما جعلنا نصل لهذه النتيجة. وإن شاء الله سأنشر كتابي بكرة أو بعد بكرة بإذن الله تعالى، أو ربما سأخره حتى تنتهي هذه السلسلة، لأنه أعتقد أن هناك معلومات ضخمة جدا جدا في هذه السلسلة تنتظرنا. فإذا هذه المعادلة تعتبر طاقة مطرودة من التفاعل. وطبقنا السيمتري الذي هو عبارة عن السيمتري الذي يقول أن كميات التحرك الداخل التفاعل يجب أن تساوي كميات التحرك خارج من التفاعل. هذا النوع من السيمتري جنى على الكتلة وجعلت أن الكتلة تتغير تغيرا كبيرا جدا، بحيث أن كتلة الإلكترون 0.5 ميجا إلكترون فولت. المجموع هم الاثنين هو عبارة عن 1 إلكترون فولت، 1 ميجا إلكترون فولت. كتلة الميون عبارة عن 106 ميجا إلكترون فولت، مجموعة من الاثنين تعتبر 212 ميجا إلكترون فولت. هذه الكتلة، الفرق في الكتل هو الذي تحمل هذا النوع من السيمتري. طيب تعال نواصل.
If you don't, then let us move on. So, I mean, what you need to do from going to here, from here to here, is obvious, right? It's something that takes maybe 10 minutes or so, but
طيب سأصور هذا قبل أن يمسح المساحة.
it's actually easy. Yes. Yeah. Simply the scalar product of two momenta, pi dot pj. Scalar product, simply scalar product, and so to abbreviate writing the full expression. Yeah. No, I mean, it's with Lorentz indices, it would be pi mu times pj mu contracted over mu. This sort of thing, which appears here. So, for example, this contracted with this. After we use the metric tensors make mu prime and mu prime equal and mu equal. So this product of the circles gives S24 times S13. Gives exactly this expression. And for example, that circle times this one gives P2 times P3 and P1 times P4. That gives exactly this expression, and so on. So from the physics point of view, it is often interesting to look at this unpolarized case, where you do not care about the spins, but of course you do care about the momenta, which tells you the angular distribution, which angles are preferred, which directions of the particles are preferred. But experimentally it's often not easy to measure the spin, and therefore we sum over. And of course, from quantum mechanics, you know that if you have quantities like the spin which are in principle measurable, you must first square the amplitude and get the probability, and then you should sum over the probabilities. You must, of course, not sum the probability amplitudes. That makes no sense quantum mechanically. And so therefore, we have squared the TFI matrix element, and after squaring, we sum over all the possible spin orientations. Both initial and final state. In this case, I mean both initial state and final state, and therefore we have summed over all 4 spins. Sometimes yes, sometimes not. It depends on the experiment. So sometimes we can control the initial state and we can polarize our E plus E minus pairs in the collision. It's not always possible, but sometimes it is possible. And sometimes, of course, we can measure the polarization or the spin of the final state particles. It might not always be easy. At the LHC, it's for sure not easy, but sometimes it is possible. And so in principle, you can measure the initial state spin and prepare it in some spin for configuration, and in principle, you can measure the final state spin. But in practical particle physics experiments nowadays, typically, both initial state and final state, you don't know the spin orientation. And then, of course, this is not yet maybe the thing that you directly compare with experiment. What one would normally do is for the initial state, of course, you know that, okay, first the question, yes. Yeah, okay, maybe I'm not the best person to ask, but I think at the LHC the detectors are not really optimized to measure the polarization of electrons. I mean, as far as I know, the electrons, for example, are measured in some calorimeters, where you basically measure the overall energy of the electrons by them heating up, or simplified speaking, interacting with some medium where you absorb the electron and then you measure the deposited energy, and so of course the information on the spin is lost in such calorimeters. For the muons, they have specific muon detectors which are at the outermost layer of the experiments, because the muons travel basically through all the other detector systems. And so in principle, maybe, I don't know, one might conceive a measurement of the polarization of muons. However, as far as I know, it is not measured. Okay, what I wanted to say something else. Okay, yes, of course, in principle, when you have this initial state beam, then you know how many particles are in your beam, but you do not know which of them is polarized such or in a different way. And therefore, normally one averages over the initial state spins. You do not sum over the initial state spin, but you take the average. Whereas for the final state, you are interested in the overall probability of producing any muons with any polarization. Therefore, you would sum over the probabilities for all possible muon spin orientations. And so, to compare with experiment, you would put a normalization factor like 1/4 in order to get the average of the initial state spin orientations instead of simply the sum. But we are not yet interested in comparing to experiment, therefore we do not care about such factors here, but only care about the fundamental quantum mechanical expressions. And that is this one. Okay, let us therefore now come to a discussion in an explicit reference frame, and that allows us in particular to look at the energy dependence. So we draw a picture. The actual physics situation looks like this. You have a collision of two beams of particles, E plus, E minus, and we look at the collision in the center of mass frame, which is typical also for collider experiments like LHC or similar E plus, E minus collider experiments, where the center of mass system is identical to the laboratory system. And then you have a final state, mu minus, mu plus. And of course, the collision happens head-on. That means the beams are on one-dimensional line. The final state particles, they also, because of momentum conservation, the momenta have to add up to 0. Therefore, they are also exactly on the one-dimensional line here. And therefore, all the four particles are in one single plane. They are in one plane, and without loss of generality, we can simply consider the xz plane, where the y coordinate is 0. And then we have here one angle theta, which describes our collision and the final state. And the angle theta is measured from the electron direction compared to the muon direction. Electron and muon with the same charge, they have an angle theta. If theta is 0, then it simply means that the electron gets converted into a muon and the direction is unchanged. If theta is 180 degrees, then the muon goes into the opposite direction, whereas the anti-muon travels in the same direction as the original electron. So let us write down explicit variables for this situation. Then we would have P1 and P2 for the electron and positron. They have the same energy in the center of mass system. And let's say the momentum is oriented in the z direction. So x and y are 0. And then in z direction we have plus or minus a variable p, simply p without index. That is then the momentum, spatial momentum of the E plus E minus pair. And the total momentum is 0 because we are in the center of mass frame. And so this three-dimensional momentum can then also be called p vector with plus minus, which is this momentum vector oriented in z direction. Then for the final state, P3 and P4, the final state energy must be the same as the initial state energy, therefore the energy is the same, E. And now we allow for this angle theta in the xz plane, so therefore we write it like this. Let's say plus or minus p vector prime, where this p vector prime is the following three-dimensional momentum. Namely, here we have sine theta times p prime, comma 0, comma p prime times cosine theta. Then we have implemented that the angle is theta, and we have also implemented that the overall magnitude of the momentum changes, p prime versus p, because of course the muon has a different rest mass. Therefore, if the energy is the same, the spatial momentum must have a different magnitude, namely smaller than for the electron. And the plus minus implements that they also fly head-on, back to back. Then what else do we have? Our variable q square, which is important, is the actual center of mass energy squared. Q square is P1 plus P2 square, which is the center of mass energy square. In this case, it is simply 4 times E square. Then our variable S13. What is our variable S13? And then also S14, which appears in the result, the scalar product of the momentum P1 dot P3. So this scalar product is first of all the energy product, E square, minus the product of the spatial momenta, which we can write with 3 vectors, P times P prime vector. But we could also write it explicitly, E square minus P times P prime without vector times cosine theta. That is the scalar product of those 2 vectors here. And actually, that is the same as the product S24. S13 is the same as S24, because P1 and P2, they differ only by the sign in the momentum, P3, P4 as well. Therefore, the product remains the same because the different sign appears squared. And so S24 is the same as S13, namely that. Then S14 is not the same. S14 is P1 with plus P here, dot P4 with minus P there. So that means now the sign is changed and we get E square plus this P times P prime vector, or E square plus P prime cosine theta. And that is, however, the same as S23. And so that means we have now explicitly evaluated all our variables that appear in the full result, and we can plug that in. And once we plug it in, we obtain an expression for our unpolarized squared matrix element in terms of explicit energies, momenta, and angles, and that we can interpret physically. But before we do that, I have to exchange the battery. Okay. Okay, so what happens if we plug in those expressions into the result at the top? Well, it simplifies in many ways. First of all, we have already seen that these two variables, they are actually equal. So we get the square of one variable plus the square of the other variable. And the square is, of course, square of that thing plus square of that thing. Some terms will also cancel out. Namely, the mixed term will cancel out. And then we have here this with q square. Q square is simply the energy square up to a factor. And here also q to the 4 gives energy to the 4th up to a prefactor. And so the result is going to be quite simple and straightforward. So the spin summed TFI square is now the following. 8 EQ to the 4th power divided by 2 e to the 4 and then times, let's write it like this, times e to the 4 plus the scalar product of p times p prime vector square plus e square times the sum of the mass squares. Okay. And so I already cancelled some prefactor because initially in the q to the 4 in the denominator you have 16 times energy square, and in the numerator you have all those prefactors 2 and 4. You can cancel them against the 16 to obtain the 2 here, and then in the bracket we have simpler prefactors. And then, as we already saw, from this first term S13 square, S14 square, we get this, e to the 4 and the scalar product squared. The mixed term drops out, and the last term immediately gives us this. So it's directly possible to understand it. So, and this is now our still general result, only specialized to the reference frame, but it's valid for all energies and all angles. And let me now make a small remark on cross-sections. So there is the notion of differential cross-section d sigma by d omega, which is a quantity which is nice because essentially it captures the physics of the squared matrix element, which is the probability. But this squared matrix element, for example, still depends on the normalization of the states, which are of course kind of arbitrary. And in particular here we have used plane wave states, momentum eigenstates, which are actually not normalized. They have infinite norm. And so therefore, to make it really physically measurable, we should divide out by the norm, and the cross-section is the appropriate quantity to do that in a well-defined way. And then let me just write what the result becomes. You get a proportionality factor, which is not of our concern right now in quantum field theory. That would be particle physics or particle theory. So let's not do that. We get a center of mass energy square in general times the final state momentum, or let's say here specifically p prime vector divided by p vector times the squared matrix element. That are the essential factors, up to some additional numerical factors which are not essential. But from the definition of the cross-section, what is essential is that you get this 1 over energy square as a prefactor, and you get this what is called a phase space factor, the final state momentum divided by the initial state momentum. So let's say that is from the definition of sigma. And you know that cross-section has the unit of an area. An area means 1 over energy square in our units. So that gives us this unit of area. And then here we have that. This is the phase space factor. And so what that means is that if the momentum of the final state particle is very, very small, then the phase space for the final state particle is also small, and you have a reduced probability because of the smallness of phase space, and so that is encapsulated in that numerator here. However, if the final state momentum is very big, you have a lot of phase space available, and then of course this factor increases. And that is the fundamental QED prediction. Which we are of course particularly interested in, but of course for the physical comparison, those factors here matter as well. So now we have calculated our fundamental QED prediction, and we can discuss it and potentially use also those other factors in the discussion. We will look at two limits, at the high energy limit and the low energy limit, and do some interesting physics discussion for both limits. And let us start with the high energy limit of this process. So what happens in the high energy limit? Or is there a question? Calculational stuff or? This factor here. Okay, I mean that will now be our discussion, right? We are now look at the high energy limit and see what the factors do. And so we come back to it. But actually your intuition is kind of wrong. The cross-sections do not rise with energy. Instead, they fall with energy, and that simply comes from dimensional arguments. If you know that the cross-section has the unit of 1 over energy square, in other words, units of an area, and if you know absolutely nothing else, if your process depends only on energy, then there is no other way. Then the cross-section must reduce by 1 over energy square. So no other dependence can arise. And that is the normal situation, which will now also appear. So let us look at it. So you have already raised very interesting and important questions, but
الكروس سكشن يتناسب عكسيا مع الطاقة. هذا طبعا يؤكد ما ذهبت إليه بصيغة جميلة جدا جدا، ويعني بكل فخر أنني يقول ما ذهبت إليه في أنه كلما زادت الطاقة كلما نقصت الأبعاد التي تحصل فيها التفاعلات، وبالتالي تخرج كتل أكبر. فالكروس سكشن يقول لنا أنه يتناقص مع الطاقة، لكن السؤال كيف تخرج كتل أكبر إذا كانت الأبعاد أصغر؟ هذا السؤال ربما نجده هنا. أنا طبعا عملت المعادلة بتاعتي وانتهيت الحمد لله، وعملت المعادلة في كتابي الفات أيضا وفيديوهاتي الفاتت، عملت معادلة خاصة بي أنها يعني كلما نقصت الأبعاد كلما زادت الطاقة، وشبهت ذلك زاد الكتل، شبهت ذلك بمعادلة اسمه من ماكس بلانك لإشعاع الجسم الأسود. تجدون هذا الموضوع في كتاب الحلقة 53. كلما نقصت الأبعاد زادت كتل، تم طرد كتل أكبر بهذه الآلية الجميلة جدا جدا. الآن هو يتفق معي في هذا الأمر، وتعالوا نشوف كيف نرى هذه الكتل. هل يمكن رؤيتها في المعادلة الأخيرة أم لا؟
In the high energy limit, we can discuss first of all what is actually a good approximation. High energy means that the energy is much heavier than the two masses of all the involved particles, and so all particles are ultra-relativistic, so they all basically move at the speed of light. Their rest masses can be neglected. The energy is extremely large, and therefore also the absolute value of the momentum P is approximately equal to the energy, since the rest mass can be neglected, and also equal to the final state momentum. So the muon momentum, the electron momentum, and the energy, they are all essentially equal. And that scalar product, P dot P prime, is then E square times cosine theta. So the scalar product of the two spatial momenta is just the magnitude of the momenta times cosine, but the magnitude is E. So that is now the approximation that we can plug in. And once we plug it in, then of course you see that everywhere there appears e to the fourth power. So in the square brackets, here you get e to the 4 times cosine squared. And that is only e to the second times rest mass. That can be neglected. That is negligible. So we
بس هنا الخطأ تم تجاهل الكتل. انظروا للكتل جميلة كيف تم تجاهلها. كتلة الإلكترون زي كتلة البروتون، لا الميون تم تجاهلها. هنا الخطأ، هنا وقع الخطأ أننا تجاهلنا هذه الكتل، وبالتالي إذا طورنا أجهزتنا سنستطيع أن قياس هذه الكتل، أو إذا عملنا معادلات بالنسبة للحدود الأخرى، بدل نجعلها لينير نجعلها دالة في حد مربعا يعطينا هذه الكتل. هنا الخطأ، هنا الذي جعل أنه لا يمكن تتبع الكتلة منذ نشأتها حتى وصول إلى هذه الضخامة. الآن احنا عرفنا أن الخطأ.
We dropped that, and those two terms are of equal importance, one with prefactorial 1 and the other one with prefactorial cosine square. And then this happens, namely the energy drops out completely. 1 over e to the 4 times e to the 4 drops out completely. So in the QED part of the expression, there is no energy dependence anymore. The QED part is dimensionless, and therefore it becomes independent of the energy. It becomes a constant. And then the energy dependence of the cross-section comes from here. So, but the QED prediction is then the following. For the differential cross-section up to unimportant factors, which are only important for particle physics, we get 1 over e square, and the phase space factor becomes 1. It becomes 1 because the initial and final state momenta are also equal, so we just get 1 over e square, and then the e times q to the 4th power times 4. The energy otherwise drops out, and then in our square bracket we only have 1 plus cosine square theta. So, and then I stress again, the 1 over e square simply comes from the definition of the cross-section, and it reflects the unit of an area. And the rest here is the QED prediction, which is dimensionless. And what does the QED prediction tell us? It tells us the non-trivial angular dependence. What probability do we get for the different angles? This is what the QED calculation tells us now, and this is the answer. This is the angular dependence and the relative probabilities of the various angles that can appear in the process. That is what we obtain here from our calculation. So, this is the only energy dependence. And I stress again, you could have guessed that just from dimensional analysis. In other words, by looking at the units of all the quantities. There is no other dimensionful quantity in the problem except for the energy, and therefore the cross-section must behave like 1 over e square. And so it drops. It does not increase. It goes to 0 in this way. And that... So, this is the only energy dependence. And I stress again, you could have guessed that just from dimensional analysis, in other words, by looking at the units of all the quantities, there is no other dimensionful quantity in the problem except for the energy, and therefore the cross-section must behave like 1 over E squared. And so it drops. It does not increase. It goes to 0 in this way. And that thing here, the angular dependence, that is from our QED calculation. Okay, so that is a nice result. And we can now also ask ourselves, is there some physical reason for this angular dependence? So it's not isotropic. The angle matters. Not all angles are equal. But the probability is always non-zero. It does not happen that the probability goes to 0 for a particular angle, so all angles are possible. But certain angles are preferred, namely the ones where theta is either 0 or 180 degrees. Those two angles are preferred. And so we might wonder, why is that? And is there maybe some explanation of that? And actually there is, and we will come to it. So we will discuss it. And angular dependencies, of course, have to do with angular momentum and spin. And so in order to understand this, we will analyze the spin and angular momentum dependence of our results and of the final and initial states. But not now. We will do that in another section. But for now, we record that we have analyzed and obtained the full result here in the high energy limit. So, low energy limit. So we need a little bit more space for the low energy limit. Or maybe not, let's try to do it here. So what do we mean by low energy limit? Now we have to acknowledge that the electron is much lighter than the muon. This comes now into play. It was not important over there, but now it's important. We concretely consider the process where we have in the initial state electrons which are light. In the final state we have heavy muons, and therefore in the low energy limit the muons are produced basically at rest or with very small kinetic energy. But the electrons, they must still have very high energy in order to produce the muons. Therefore, we can still neglect the electron mass, and as a good simplification, we set the electron mass to 0 here in this analysis. But we say that the overall energy is approximately equal to the muon rest mass, and so that then tells us that the muons are produced more or less at rest. They are approximately at rest. So, and then you know that actually the more precise version of the energy is this, namely we have the muon rest mass plus non-relativistic approximation p prime square for the muon momentum square divided by 2 times the muon mass. That is, of course, the non-relativistic kinetic energy relationship, right? And that is a good approximation if the muons have small non-relativistic momentum. And so there would be higher order terms which are neglected. And that is also the same as the simple thing, muon mass times the velocity divided by 2. And so I call now V prime the velocity of the muon. Let's say velocity V prime, which is much smaller than 1, in other words, much smaller than the speed of light. So then this is our expression for the energy, and then the other expression that we need is the scalar product of our 2 momenta, momentum of the electron dot momentum of the muon, P P dot P prime. And so for the muon momentum, for the electron momentum, the magnitude is still the energy because the rest mass of the electron has been neglected. And for the muon, we have this magnitude P vector prime square and then times cosine theta. So and this is of course the same as E square. The momentum is given by energy times velocity times V prime times cosine theta. So the momentum is given by velocity times rest mass non-relativistically, but the rest mass is approximately equal to the energy. So therefore the first approximation, that is equal to energy times velocity. And then we have all our variables and we can plug in again into our initial formula, which is still at the top of the blackboard over there. And then we obtain the following. D sigma by d omega is, so now 1 over E square times that phase space vector P prime over P. P prime over P, what is this? That is now the momentum of the muon, which is energy times velocity divided by the energy. So this is just the velocity times V prime. That is the phase space vector. So our phase space vector is now not 1, but it's the velocity, and the velocity is by definition small. Then we have, what else do we have? 4 times EQ to the 4th power. And then our square bracket is now the following. So E to the 4th drops out again, and then we have from the first term we have 1. From the third term we have E square times the muon mass square. E square times muon mass square is also E to the 4th power approximately, because the muon mass is equal to the energy. The electron mass drops out, and so therefore we get 2 times E to the 4 from both terms, and E to the 4 drops out. And then we have the scalar product, P dot P prime square. P dot P prime is also E to the 4th times velocity square times cosine square. So we have plus the term proportional velocity square times cosine square theta. So let's not worry about the prefactor. So now I want to get a little bit of space, not much, but let me just remove this here. So, the square bracket. To first approximation or to 0th approximation in the velocity, the square bracket is 2. The velocity is very small, so to a very good approximation, the square bracket is simply 2. 2 means independent of the angle. So now we have an isotropic production of mu plus mu minus. The angle doesn't matter. It doesn't matter to a very good approximation because the velocity terms are suppressed and only the velocity dependent terms depend on the angle. So, and the angle independent term is actually non-zero, and therefore we have to a good approximation isotropic production. So we have approximately constant independent of the angle. So, and now a little bit more general remark. We could in principle expand this cross-section in spherical harmonics or Legendre polynomials, PL of cosine theta. And maybe you remember doing this sort of thing in quantum mechanics too, where we also discussed.
طبعا هنا دخلنا في الشغل حقي أنا. هذا هو شغلي أنا. هذا هو شغلي أنا. وقد عملت فيه فيديوهات كثيرة. قبل أن يتحدث هو أنا أريد أن أوضح شيئا عن شغلي هذا. شغلي أنا قدمت أن الفضاء مقسم أو سلايتد، أو مثلا نقول أنه في شكل مدارات مثل مدارات الذرة، تتحكم في هذه المدارات الكتلة أو طاقة التفاعل أو مجموع الكتل أو مجموع كميات التحرك. المهم هذه المدارات تتحكم فيه الكتلة أو طاقة التفاعل. كلما تقربنا من الكتلة أو كلما زادت الكتلة كلما زادت طاقة التفاعل أصبحت المدارات قريبة من بعضها البعض. أصبحت المدارات قريبة من بعضها البعض. تقارب المدارات هذا يعني أن التفاعل متقارب أو طاقة التفاعل عالية جدا، وبالتالي تتقارب المدارات هذه تطرد كتلة أكبر. أنا كنت أريد أن أشبهها بالإلكترون، لكن نحن نعلم أن الإلكترونات تتعامل بالطاقة وليس الكتلة، بحيث أنه الطاقات القريبة من النواة تكون أكبر من الطاقات البعيدة من النواة. يعني مثلا في مدار كي الحركة أو العملة التي يتعامل بها الإلكترون هي الإكس راي. إذا أنت أردت أن تحرك الإلكترون في مدار كي فإنك تعطيه إكس راي. لا تستطيع أن تحركه بطاقة ضعيفة مثل الضوء المرئي، يجب أن تديه إكس راي. بعيد عن النواة مدار ال مدار ام يمكن أن تحركه بضوء مرئي ومائل إلى الأحمر. في المدار الجزيئي طبعا أكبر من الذرة. في المدار الجزيئي أنت يمكن تحرك الإلكترونات بالطاقة تحت الحمراء، تعمل اهتزازات في الجزيء على مستوى الطاقة الرابطة، على مستوى الروابط. فكلما بعدنا عن الذرة عن النواة كلما قللنا الطاقة لطاقة الفوتون من أجل تحريك الإلكترون. هنا أيضا لكن الأمر لا يتعلق بالإلكترون إنما يتعلق بالكتلة. كلما تقربنا من محتوى التفاعل أو منتصف التفاعل كلما كانت طرد الكتل أكبر، كلما بعدنا كان طرد الكتل أقل. في النتيجة هي مشابهة، لكن هناك تتحدث عن الطاقة وهنا تتحدث عن الكتل. فهذا هو تفسيري للتفاعلات دون ذرية. تقليل الأبعاد يعني كتلة أكبر، يعني طاقة أكبر، يعني كتلة أكبر، وهكذا. طيب، وهذا ناتج من أن الكون ثنائي الأبعاد يكسر هذه الطاقة بطريقة أكبر. يعني زمان كان طاقة بسيطة يقوم بكسر هذه الطاقة في أطرافها في أشياء قليلة، لكن الطاقة كبرت فكسرها يكون بطريقة أكبر. هذه الطاقة تتكثف وتظهر في شكل كتلة، تعطينا كتلة أكبر، وهكذا. طيب، تعالوا نشوف هذا التشابه وما سيذكره الدكتور في هذا الموضوع.
And one good way to this a little bit more general remark. We could in principle expand this cross-section in spherical harmonics or Legendre polynomials PL of cosine theta And maybe you remember doing this sort of thing in quantum mechanics too, where we also discussed scattering. And one good way to discuss and analyze scattering was to expand in terms of spherical harmonics, or if we are in a plane, only the Legendre polynomials are sufficient. They form a basis of all functions depending on the angle, a very useful basis which is organized according to angular momentum, higher and higher angular momentum. So if you do this expansion here, then you see that the square bracket has immediately actually this form. It has a form with a constant which corresponds to L equals 0, and it has a term with L equal 2. There is apparently no term with L equal 1, but there is a term with L equal 2, and the L equal 2 term happens to have a prefactor v prime square, so the L equal 2 term is suppressed with the velocity square. So, and that is actually clear. Why is that clear? It is clear from the initial expression, because in the initial expression we have a function of p prime, the vector p prime. So the velocity only enters the whole result via the variable p prime. But the variable p prime, the variable p prime depends on the velocity and on the angle simultaneously. Therefore, it is clear from that structure and also from this structure that the velocity and the cosine theta appear always with the same power. The fundamental dependence is on p dot p prime, which is then proportional to v prime times cosine theta. Therefore, PL cosine theta is suppressed by v prime to the power n in general. And here, of course, it's a polynomial, so it stops at L equal 2. But in general, you would immediately know that the higher L's, the more complicated angular dependence is suppressed by higher and higher powers of the velocity. And therefore, if you're interested in the dominant effect, you should ask yourself, what is the lowest L that appears in the result with a non-zero coefficient? And here it happens that L equals 0 already appears with a non-vanishing coefficient, and therefore, to a good approximation, the angular dependence is a constant. From lowest non-vanishing L, and here that is L equals 0. And since we have here a non-vanishing contribution with L equals 0, we call that S-wave scattering. So to a good approximation, we can approximate everything with the L equals 0 term, and which has the name S-wave for whatever reason, and therefore this is S-wave scattering. And so now you can imagine that there could also be something like P-wave scattering, where the lowest L somehow vanishes, maybe for some symmetry reasons, and then the dominant effect would come from the first non-vanishing L, which might be L equal 2 in this case, and then the angular dependence would come from the Legendre polynomial with L equal 2. And so in this way, you see that it's actually kind of useful and neat to approximate or expand such cross-sections in terms of these angular dependent functions in order to get a deeper understanding of what happens. And here the understanding tells us that we do have S-wave scattering, so there is no preferred angle. The angular dependence is trivial and a constant. Okay, very good. So now that's it. We have 5 more minutes, and in these 5 more minutes you can either ask a question or I summarize the whole thing.
إذا من هنا عرفنا أنه هناك يسمى S scattering و L scattering مثل المدارات بالضبط. مدار S ومدار L. مدار S يتميز بأنه دائري، ومدار L يتميز بأنه في شكل محاور متعامدة على بعضها البعض. مدار دي يتميز بأنه لديه زوايا قطرية وهكذا، وبالتالي نجد أن فضاء الإلكترون حول الذرة هو شبيه تماما لفضاء التفاعلات داخليا في التفاعلات الداخلية، وهذا ما يؤكد وحدة الفضاء. فضاء موحد في جميع الأبعاد، أبعاد كبيرة وأبعاد صغيرة كل واحد. حتى الشمس، ينظر إلى الشمس والأرض، الشمس والكواكب والمجموعة الشمسية تدور في بلين واحد اللي هو في مدار اس. هل هناك كوكب يدور في مدار ال؟ نعم. نرى انه المذنبات تدور في شكل اسطواني او شكل إهليلي او شكل اسطواني شبيه بالاسطوانة. فهو هذا مدار يعتبر مدار ال، لكن بطريقة معينة. هل هناك مدار دي؟ ربما يكون هناك مدار دي، لكن الكواكب في الأبعاد الضخمة أيضا تظهر، لكن ليست بالقوة التي تظهر فيها الإلكترونات والقوة التي تظهر فيها في فضاء التفاعل عميقا داخل التفاعلات. فربما نجد أن الكواركات تدور بهذه الآلية، ربما يكون ذلك، وربما نجد أن تحت الكواركات أيضا هناك جسيمات ما داخل الكواركات تدور بآلية معينة وهكذا. يعني شيء غريب جدا، لأن الفضاء موحد ومتساوي وخواصه متساوية كليا، فشيء غريب جدا.
Once again, always start a new topic. Yes, please. The probability, yes. The zero does not come from the probability amplitude. That cannot know this, but it comes from the phase space here. The phase space will go to zero. If you are below the threshold, then the phase space factor is identically zero. And another way how this would become zero is with the momentum conserving delta function, which is not part of the expression because we have factored it out. But the momentum conserving delta function cannot be fulfilled if you are below the threshold, because then the final state energy must always be above the muon mass twice, whereas the initial state energy is below it, and therefore the delta function would be zero. Therefore, the delta function is the reason within the matrix element calculation to make it zero, and then there would also be a zero coming from the phase space. But this expression here is analytic. It's an analytic function of the momenta and energy. And as you know from function theory, if you have an analytic function which is non-zero for some values of energy and momenta, it cannot be zero below a certain threshold. I mean, it's analytic, therefore it will not vanish anywhere. Yeah, if you say P prime is imaginary, then of course you have evaluated that momentum conserving delta function, and therefore you would say it's imaginary, and so the expression then becomes meaningless. But if you simply say, I regard this as a function of energy, P and P prime, for some values of those three variables, then the expression is analytic in all three variables, and you do not see that it corresponds to a kinematically impossible process. That is right. So that is the delta function. The delta function makes it vanish. Okay, plus the requirement that the momenta are real. So the momenta must be real, and therefore the delta function has to vanish. It vanishes. Other questions? Yeah. Real and for the delta function has to vanish. It vanishes. Other questions? Yeah. Here, the result will receive some further terms with a more complicated dependence on all variables, but I do not know by heart how the terms look like. But of course, there are, first of all, more complicated functions of the angle, which could be expanded. So then in the higher order terms, maybe the expansion is not only a polynomial, but you will get more complicated functions of the angle, where still, however, that argument holds that I made. And otherwise, there will be also more complicated functions appearing. For example, there can be often logarithms of certain quantities in higher order results. Logarithms of e squared divided by something else, maybe logarithm of e squared divided by the muon mass square. Such terms can appear. This is a typical feature of higher orders in quantum field theory. And so the analytical structure of the result changes. And otherwise, simply, of course, all the coefficients will be modified by terms of higher order in the coupling, because perturbation theory is a power series expansion in the coupling constant, and so all coefficients might get perturbative higher order corrections. And such new features will appear. Yes, that is what I mean. So of course it will remain the case that the result can be expressed in terms of those variables, because these are the only variables in our theory. And for example, for the low energy case, the same argument remains true, namely that the result can depend only on that combination here, and therefore maybe now the cosine will even appear in a logarithm, but you can then do a Taylor expansion of the logarithm around some value, and then you have this connection between the velocity and the cosine theta terms also at higher orders. No, I mean, of course it's optional, but you can see maybe in this way the structure of the result or the feature, and you can analyze sort of S-wave, P-wave scattering, and you can label different processes with these names in order to get a more intuitive picture of what happens. But of course the result is what it is, so you do not need to expand it in order to see. So here you see this constant behavior, but I wanted to point out the relationship between this and what we did in quantum mechanics too, because sometimes you see indeed simply the statement, this process involves only P-wave scattering and the S-wave part is 0, and then you know what that means. Then, for example, the 2 would be absent, and then you might have only a cosine square dependence. And if that is true, you know that the cross-section, the probability is much, much smaller, right? The probability is much, much smaller because at threshold you do not start with a constant, but you start with velocity squared, which is at threshold is 0. You have a much, much weaker rise of the cross-section above threshold. And that is, for example, important for dark matter phenomenology, because in dark matter you have different candidate particles which could form the dark matter in the universe. And the dark matter must annihilate in the early universe in order to, let's say, bring the relic density down to the value which is observed today. And therefore you need a cross-section for the annihilation of dark matter, and various candidates have exactly this feature. Either they do have S-wave scattering, or they only have this P-wave scattering. And those dark matter candidates where you have S-wave scattering, they have, so dark matter is non-relativistic, like planets and stars in the universe, so dark matter particles collide with very small speed. And if the constant term is missing, the collision probability is extremely small. And so dark matter particle candidates where this S-wave part is missing you have a difficulty in explaining why the relic density reaches the value that we see. Whereas if you have this S-wave scattering, the cross-section for dark matter annihilation is much higher, and so that helps in explaining the dark matter relic density. So this sort of thing is, for example, often discussed in the literature. Therefore, it's an interesting and important discussion. Yeah.
طبعا بالنسبة للمادة المظلمة، أنا لدي تفسير آخر من هذه المعادلة. يمكن نستخلص تفسيري من هذه المعادلة. عند المادة المظلمة هنالك طبعا أولا تأثير الكتلة وتأثير الشحنة تقل. لماذا؟ لسيطرة الفضاء ثنائي الأبعاد. فضاء ثنائي الأبعاد لسيطرته يجعل تأثير الكتلة وتأثير الشحنة يقل من التفاعل أو في هذا الفضاء، وبالتالي تقل تأثير الشحنة. قل تأثير الشحنة يعني هنا EOC4 تعتبر الشحنة 10⁻19 ستكون أقل من ذلك، وبالتالي هذه ستؤثر على probability مباشرة. الشيء الثاني، هذه الطاقة تمثل طاقة التفاعل، وهذه الطاقة كما قلت كلما زادت هذه الطاقة كلما تعمقنا في التفاعل كلما أنتجت مواد أو كتل عالية. طيب إذا كانت هذه الطاقة صغيرة فهذا يعني التفاعل لا يكون كبيرا، وبالتالي هذا يعطينا كتل صغيرة، وإلى درجة أنه يمكن حذف، يعني ممكن تجاهل هذه الكتل أو ممكن أن لا نراها. طبعا على حسب عكس هذه المعادلة تقول أنه الطاقة إذا صغرت، هذه الطاقة صغرت هي موجودة في المقام ستكون في البسط برقم كبير، وبالتالي كروس سكشن سيكون كبيرا. لا، الأمر معكوس في نظريتي، لأنه نحن افترضنا قبل قليل أن الطاقة كلما صغرت هذه الطاقة يعني المسافات تصغرت يعني تولدت كتل أكبر، وهذا أقصد الطاقة كبرت كلما كبرت الطاقة صغرت المسافات وتولدت الكتل أكبر. صغرت المسافات، ما هي المسافات؟ هي المسافات اللي هي المدارات في الفضاء. تخيل أنك لديك مدار كبير، يعني مدار، الفرق بين المدار والمدار بقدر الغرفة. طيب أنت تحتاج هذا المدار الكبير أن يصطدم فيه فوتون اللي ينتج لنا مادة أخرى. هذه المادة نستطيع قياسها بالتلسكوبات مثل توهج، يحصل سكتر مثل التوهج يعني، وهناك مدار كبير جدا. فكم فوتون يستطيع، يعني يمكن أن يخطئ هذا التصادم، المادة المظلمة يخطئ هذا التصادم بسبب كبر هذه المدارات. هذا مقصده، هذا بالضبط مقصده. فأنت تحتاج إلى مدارات أقل، كلما صغرت المدارات كلما كان التفاعل أقوى، أو العكس صحيح، كلما كانت الطاقة أكبر كلما صغرت المدارات كلما ظهر التفاعل أكبر. فهذه هي نظرية ما تقوله. فلدينا هنا احتمالي، وليس احتمال إنما لدينا حدين يؤثران بدرجة كبيرة في ظهور المادة المظلمة. الحد الأول هو الشحنة الآن موجودة هي، وهذه الشحنة تكون أقل من ذلك لأن الفضاء ثنائي الأبعاد يقمع تأثير الشحنة. يعني بدل ما 10 سي تكون 10 سي ناقص 19 تكون 10 سي ناقص 24 مثلا. وأيضا الطاقة 1 على إي تربيع، أيضا نفسرها بهذه الآلية أنه كل ما زادت الطاقة نقصت المدارات، كل ما نقصت المدارات كل ما كان التفاعل أقوى. طيب كيف نعالج موضوع الطاقة؟ شرحت ذلك في فيديو. نعالج موضوع حتى الشحنة يمكن نعالجهما بموضوع في غاية الأهمية، وهو أن نتتبع موجات جاذبية 1، لأن موجات الجاذبية عبارة عن طاقة مكثفة في فضاء، فموجات الجاذبية عندما تمر بهذا المنطقة التي فيها مادة مظلمة وصدف أن هناك إشعاع ضوئي، فإن الإشعاع الضوئي يظهر خصائصه. الشيء الثاني والأهم هو أن نرى ضوء قوي جدا جاي من الكويزر ولا من البلسر. هذا الضوء القوي جدا يستطيع أن يعادل النقصان الذي يحصل في الشحنة والنقصان الذي يحصل في المدارات أو الزيادة في المدارات. يعني مثلا بالنسبة للشحنة لديك بدل ما كان لديك 10 فوتونات أصبحت لديك 1,000,000 فوتون، وشحنتهما الشحنة صغيرة، بالتالي 1,000,000 فوتون يمكن أن تعادل هذه الشحنة الصغيرة. الشيء الآخر إذا كان لديك مدارات كبيرة لكن لديك عدد أكبر من الفوتونات، ربما هذا العدد الكبير من الفوتونات ذو الكثافة العالية يغطي لك هذه المدارات بعيدة من بعضها البعض، وبالتالي تظهر خصائص التفاعل بين الفوتون والمادة. إذن عندما يكون هناك ضوء قوي جدا من كويزر ولا من بلسر ولا من أي شيء، هذا الضوء القوي جدا حتى السوبر نوفا، هذا الضوء القوي جدا يمكن يظهر خصائص المادة المظلمة. أو لديك موجة جاذبية قوية جدا، موجة كبيرة جدا تسير في تلك المنطقة، هذه الموجة تعمل انضغاط للفضاء، وهذا الانضغاط يجعل كيرفيتشر يزيد. طبعا المادة المظلمة تزيد مع الكيرفيتشر وتنقص مع نقصان الكيرفيتشر، فتجعل الكيرفيتشر يزيد، وهذه زيادة الكيرفيتشر يجعل خصائص المادة المظلمة تظهر جليا. وهذا واضح أننا يقولون أننا نريد أن نتتبع المادة المظلمة من خارج المجرة إلى داخل المجرة في وسط المجرة، يبحثون عن مادة مظلمة في وسط المجرة. لا يمكن أن تجد مادة مظلمة في وسط المجرة، لأن الفضاء صنع الأبعاد وسط المجرة اللي هو بالقرب من الثقب الأسود الضخم، فإن الفضاء صنع الأبعاد يكون قليلا جدا، والتأثير أكبر يكون في الفضاء رباعي الأبعاد، وبالتالي يظهر تأثير المادة العادية وليس المادة المظلمة. هذا تفسير بالنسبة للمادة المظلمة.
Okay, no, I mean, you're right. I mean, the Legendre polynomials, they have this they are polynomial constant plus cosine square. The main thing is always the highest power is, of course, L. So each Legendre polynomial of some L gives you a certain angular dependence, and the intuitive picture is always that if you look at the polynomial with number L, and you vary the angle, you go in a circle once, then you have L maxima and minima of your angular dependence. So the higher the L, the more weakly your angular dependence becomes. That is the intuitive picture, and so the constant doesn't really matter, doesn't disturb this thing. Anyway, the higher powers are suppressed by V squared. That is the point. That is the point. So only if you have this S-wave scattering and L equals 0 appears, you have this constant non-velocity suppressed additive piece here in the cross section. Okay, then let us go on tomorrow. By the way, just in order to avoid confusion, tomorrow there will be a lecture. I don't know whether it was planned like this, but anyway, tomorrow there will be a lecture. Good, and then we will look at the spin dependence of this whole thing. So see you then.